My name is Chris Hickson. I'm the student teacher for mathematics in the middle school at Miles ELC, and this is the 7th period study guide. So, I'll be straightforward with you, 7th period. I forgot my copy of your study guide in the classroom, but that's okay. We're going to go ahead and talk about each of the 3 topics that are going to be on your exam on Tuesday, and um, this should still give you a good idea of what it is that we're looking for on this exam. So the first topic of the exam is determining if something is a function. The definition of a function I have there, a function is a special relationship where each input has a single output. This is really important. So we're looking for all of the inputs of the equations and making sure that for each one of those inputs there is only one output. If we can verify that, then we can prove that this is a function. So the first way we would see this kind of question presented to us is in a graph. And so I'll go ahead and give you an example of what the graph looked like on your study guide. So the graph looked something like this. So in this case, with graphs, you can do the vertical line test. You would take a line and you would draw it straight down. And if it only intersects with the graph one time, that would indicate that it is a function. But remember, that has to be true at all intervals of the function. So, for example, if I do the line test here, and it only crosses one time right there, I can't then just say that this is a function. I have to test it essentially all over the graph. So I can do this multiple times, and it's not an issue until we get here. But you'll notice if I were to do one like there, for instance, it would intersect with my vertical line would intersect with our function 3 times. So this lets us know that it is not a function, and we could write something like it isn't a function because it doesn't pass the vertical line test. You could even say here that it's not a function because each input doesn't have only a single output. Because here, this input of x, let me get a different color here. So for this input of x right here, I get the x-axis keeps going. For this input of x right here, it actually has 3 different outputs for y. And so remember, we're trying to make sure that each input has a single output, but this input has multiple outputs. Let me give you another example. So here's another graph. And before we do the vertical line test, we can look at our input values, which are along the x-axis here. And you'll notice that each one of these input values only has one output. If I look at the input here, it only has one output exactly right there. If I look at the input here, its only output is right here. It's not having an output more than one time. So this is a function. So if we do a vertical line test, we can prove that each time we draw a line, we're only going to intersect with this function a single time. And I think it's important to notice that if you look at, for example, the y values here, the y values are going to be the same here and here, but the x values are going to be different. It's okay if y values are the same. A single y value, in this case, let's say this is 3. A single y value can have multiple x values associated with it, but a single x value can't have multiple y values associated with it. So again, for the same reason, this is a function. And we use the same reasoning we did up here, except for it did pass the vertical line test. Alright. So that's how to determine whether or not a graph is a function. The vertical line test is pretty reliable. So let's talk about tables. I don't remember the exact table you had, but I will go ahead and make one up. The rules for identifying whether or not a table is a function should remain the same, no matter what your table is. So when we're looking at our function here in table form, we want to look at the input values, because remember, the definition of a function is that each input only has a single output. So if you'll notice, we've got a bunch of different inputs here. One of the big hints that this is a function is that none of the inputs are repeating. So we've got -1, 0, 1, 2, and 5. Those are all different numbers. That means that our inputs aren't repeating. And if we look at our output, each one of our inputs only has one output. -1's input only has a -6 as its output. 0 as an input only has 1 as an output. 1 as an input only has 0 as an output. 2 only has 1, and 5 only has 2. And what you guys might have noticed is that there is a 1 here and a 1 here. That's okay, because each one of these inputs, the x values, only has one output. But each output, in this case 1, the output of 1 has more than one input. The 1 is connected to the 0, and 1 is also connected to 2. That's okay. Remember, our definition does not bind us to having only one input for each output. It's each input has only one output. So really, we're looking at the x values on our table, and we want to make sure that each one of the x values only corresponds to one y value. So yes, this is a function because each input has only one output. So if you guys want to go ahead and pause this video, I'm going to erase this and we're going to do another example. Alright, let's come up with a different example. So I'll just make another table. So when we look at this table, one of the first things that sticks out, remember we're going to examine the input values, the x values, is that the x values are repeated here. And I'll go ahead and circle those. So we've got a -2 here as an input value, but it also comes up here as an input value. -2 as an input corresponds to -8, but -2 as an input also corresponds to 8. So let's see what this might look like on a graph, because that's usually a red flag that this is not a function. So if we look at -2, we'll just say that's right here. And we'll say that 8 is up here. So -2 corresponds to 8. It gives us that point. and negative 2 also corresponds to negative 8, and we'll say that's down here. So as you can see, my graph's a little tilted, so it's not exactly straight, but if we were to do a vertical line test, that vertical line would go through both of these points. And that, as we learned up here, means that this is not a function. And we can verify that in the table because each one of our inputs does not correspond to only one output. Negative 1 has only one output, 0 has only one output, and 1 has only one output. But negative 2 has two different outputs. Negative 2 gives us a negative 8 and an 8. So no, this is not a function. Because each input does not have only one output. Most of them do, but negative 2 did not, so therefore this is not a function. Alright, let's talk about equations. This threw some people off in our work, and so let's talk about what we need to do in order to determine whether or not an equation is a function. So let's take the equation 3x minus 2. And in order to do this, we need to think about a couple of things. First, we need to think about are there any restrictions on numbers we can put in as inputs or numbers we can get out as outputs? And then we also need to look at the graph. So let's go ahead and just do a basic graph of what this might look like. Well, we know that this is in the form y equals mx plus b, so this is a line. X is to the first power, so we know that this is a linear function. We know that our b value, or our y-intercept, is negative 2, so it's going to cross down here. I'll use a different color. It's going to cross down here. And this is a positive slope, so we know that it's going from left to right in an upward trend. So I don't know what this exactly looks like. We could make a table, but I'm not going to do that because it's not really going to matter for what we're doing. So you don't have to make a table, but you know that it's going to look something like this. Now it could be angled a little more or a little less. I'm not sure. I would have to actually make a table. But for what we're doing, this is totally okay. And we know that this just goes on and on forever. So before we get into that table, let's think about the equation here. Are there any numbers you can come up with that can't be plugged into this? Is there some negative number that can't be plugged into this that won't work if we put it in there? And there isn't. Can we plug 0 in there? Yeah, we could totally plug 0 in there. We would just get negative 2. We could plug in any positive number in here and we would get an answer. So there isn't a limitation on what we can plug in. So x has no limits. So then we have to think about our outputs. Are any of our inputs going to give us more than one output? For example, if I plug in negative 2, am I going to get two different answers like we did up here? So if you plugged in negative 2, you would just get this. 3 and negative 2 would be negative 6. Minus 2 more would be negative 8. So you don't have to do this, but the point I'm making is that you would only get one number. Every time you plug something in here, you're only going to get one answer. And that's because this function is linear. No matter which x value I plug in here, it's only going to have one output. And we can prove that by doing the vertical line test. It's going to pass it each time we do it. And that's because this is a function. This is a linear function. So we can say that, well, let me erase this so we've got a little room to write. Let me make my eraser bigger. There we go. So we can say that, oh, whoops. Yes, this is a function. each input has exactly one output. Whoa. So again, you can pause this if you want to write this down, but I'm going to go ahead and erase what I have here to talk about another scenario. Oh, my eraser's tiny again. There we go. All right, so let's talk about this scenario. And again, we'll talk about our limitations, and we'll also talk about the graph itself. So let's go ahead and graph it. Actually, let's go ahead and look at our limitations first. Are there any limitations on what we can plug in? Well, we know that we can plug in any large positive number. If we put in like 10,000, we could totally do that. If we put in 0, we can do that. But we can't plug in negative numbers. So we know we're limited to the positive half of our x values, and that's okay. We can still determine whether or not this is a function. But it's important to note that. In terms of answers, we can get any answer we want. We can get positive and negative answers. So we're not too worried about that. But now let's look at what happens with this graph. And what we can do is we can make a little table that will help us graph this if you're unfamiliar with an x squared graph. And we'll just take numbers that can be easily, or excuse me, a square root of x graph. We'll take numbers that can be easily square rooted, just so our answers don't get kind of crazy. So the first square root that I can think of would be 1. And the square root of 1 is either 1 or negative 1. Because remember that the square root of 1 is just asking us what number multiplied by itself is equal to that number. So 1 times 1 is equal to 1, but negative 1 times negative 1 is also equal to 1. So the next one that I can think of off the top of my head is 4. And if we took the square root of 4, we would get 2 or negative 2. And then the next is 9, which would be 3 and negative 3. So if we graphed this at 1, it would be positive 1 and negative 1. At 4, it would be positive 2 and negative 2. And at 3, it would be, or 9, it would be positive 3 and negative 3. But notice if you plugged in 0 here, the only answer you would get is 0. Because positive 0 and negative 0 are the same thing. So our graph, let's see if I can connect the dots on this equipment, would look something like this. So each one of our inputs, with the exception of 0, because 0 is kind of a funky number, with each one of our inputs is going to give us exactly 2 outputs, which, as you recall, violates our rule where each input must have a single output. None of these inputs, except for 0, have a single output. They all have multiple outputs. And we can, again, prove that by doing the vertical line test on this graph we have over here. If I drew the line here, I would intersect my function twice. So this is not a function. Not a function. Not all inputs have only one output. And you can write that like this, or you can write it how we did up here. Each input does not have only one output. It's basically saying the same thing. You just have to communicate to me that not each of the inputs is bound to only one output. That's the big deal with defining whether something is a function or not. Alright, so if you want to pause here, that's awesome. If not, that's cool too. We're going to jump into the next section, which is function notation. Alright, so I've got some functions here. I have an f of x function. I have a g of x function. And I have an h of x function. So when we're evaluating things, it's important to figure out which function we're using first and then evaluate from there. So let's say, for example, it said f of -2. Well, we have to first find our f function, because it's asking for f, asking for us to take the f function. This is the f function, so let's go ahead and write that down. But it's asking us to evaluate this f function at -2. So for every x value, we'll instead write -2. So every time I come across an x value, oh, there's one, I'll write a -2. Now that I've done that, I can go ahead and solve this. We want to follow the order of operations, and I'll go ahead and write that here just to save it for the rest of these, just in case you forget. Looking at this, the first thing that comes up in order of operations is parentheses. There are no operations inside of our parentheses. We've got it down to just a single constant. So we don't have to worry about doing any operations inside the parentheses, so we can move past parentheses. The next step is exponents. We do have an exponent here. And one of the things I noticed, there are a couple of common issues. A lot of students either didn't do exponents correctly. For example, let's take this for example. This is -2 squared, which is going to be -2 times -2, which I'll show you in a second. So we'll get into that in a second. I'm sorry. Let's back up. So the other common issue is people did 3 times -2, but you don't want to do that. That's not the way you want to do this, because that will get you the wrong answer. So make sure you're not doing that. That would be if we were doing multiplication before exponents, but we don't do that. So we're going to address the exponents here, and -2 squared is the same as -2 times -2. A lot of people did -2 times 2, which will get you -4. But -2 times -2 is actually going to be 4. So be careful when you do your exponents. A lot of people messed up on that. We're done with exponents here, so now we can move on. Multiplication and division are next. 3 times 4 is 12. We're left with 12 minus 4, which is 8. So f evaluated at -2 is equal to 8. Alright, I'm going to erase this one, so if you're still writing, that's cool. You can go ahead and pause the video, but I'm going to erase this and do another example. Alright, so let's take h of 6. So first we have to find our h function, which is right here. And our h function is x divided by 2, quantity squared. So now, each time we see x, we're going to replace it with 6. So h of 6 is going to equal 6 divided by 2, quantity squared. We're going to address the inside of our parentheses first. You don't want to square 6 squared here. You don't want to do that. 6 divided by 2 is 3. So h of 6 equals 3 squared. Now we can square it. H evaluated at 6, or h of 6, is 9. Alright, you can go ahead and pause it here. I'm going to erase this and do another example. Alright, let's look at, what if we did, oh, whoops, wrong color. What if we did h of g of, let's do 4. So we're evaluating the function h, evaluated at the function g of 4. So let's first look for our function h. So here's our function h. So we're going to be taking this function and evaluating it at g of 4. So the first way we can do this, the way I suggest doing it, it seems more complicated, but in the long run it'll pay off when you get to more complicated math. My h function is x squared, or x divided by 2 squared. So it's going to be x divided by 2 squared. But we're evaluating this at g of 4. Remember that h is being evaluated not at x like it is here. It's being evaluated at g of 4. So we've identified our h function. Let's go ahead and erase this. And let's look at that inner function. So we can't just evaluate this at x like we have here, because this isn't evaluating it at x. This is saying h of g of 4. So let's take the inside, g of 4, and let's do that. We know that our g of x function is here. And we've got x plus 2 squared plus x. But it's asking us to evaluate it at 4. So every time we come across x here, we're going to plug in a 4. So we'll have 4 plus 2 quantity squared plus, and there's another x here, so we'll add another 2. Or, whoa, excuse me, we'll add a 4. I don't know why I added a 2 there. There we go. So now we have our g function evaluated at 4. But remember that we're taking this and using this to evaluate h. So if you recall our h function, which we wrote down earlier, which is this, we're going to plug all of this in to h. So this entire thing is going to become our x value. So if we pretend that this whole thing is x, and then we divide it by 2, right? And then we have to take this whole thing, like we have here, and we have to square it. So let's do that. So now we'll just work from the inside. 4 plus 2, give us a little bit more space here. 4 plus 2 is 6. So on the inside, well, we'll write everything else out real quick. So 4 plus 2 is 6. So we've got 6 squared plus 4, and then all the rest of this. So now we can do 6 squared, which is 36, plus 4, divided by 2, quantity squared. 36 plus 4 is 40. And some of you might be saying, whoa, 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 Chris, why aren't you doing the division first? And that's because this division bar here is a way of grouping. This is, when I have it written like this, where both things are above the 2, this is really something like this. So we have to do this first. 36 plus 4 is 40. Excuse me. So I'll write that over here. 40. And then I'll write the rest of it. Now I can take 40 divided by 2, which is 20. And now we can square it. Now we've gotten rid of this fraction. We're just left with 20. 20 squared. Let me just multiply those. Remember, again, the big mistake here people did was doing 20 times 2. That is not what this is. 20 squared says 20 2 times multiplied together. So we'll just leave a placeholder here. 2 times 0 is 0. 2 times 2 is 4. This is 400. So h of g of 4 is equal to 400. Alright, take a minute to make sure you got all of this down, and I'm going to go ahead and erase. Alright, so let's do another example. Let's take, we'll do, oh, get the right color. We'll do f of 3 minus g of negative 4. Let's do that. So the first thing we're going to do is we're going to evaluate our functions individually and then just solve for them. So the first thing we need to evaluate is f of 3. Well, our f function is here, so we'll have 3x squared minus 4, and I'll do that down here. But instead of x, we're evaluating it at 3. Three squared is 3 times 3, which is 9. 9 times 3 is 27. 27 minus 4 is 23. So we'll write that up here. Instead of f of 3, we found out that f of 3 is equal to 27, or to 23, excuse me. Now we'll look at g of negative 4. Well, g is this function right here, x plus 2 quantity squared plus x. So I'll write that down here. Let me write that a little bit clearer. Well, actually, you know what? Well, let's just erase that and rewrite that. We'll erase this too. So it's x plus 2 quantity squared plus x. And we're evaluating it at negative 4. So negative 4 plus 2 quantity squared plus negative 4. Negative 4 plus 2 is negative 2. Plus negative 4 just becomes minus 4. Negative 2 squared is negative 2 times negative 2, which is just going to be 4 minus 4 is equal to 0. So g evaluated at negative 4 is 0. 23 minus 0 is 23. So f of 3 minus g of negative 4 is 23. And there's another way we can do this. If you don't want to go through and individually do these things, you can put them all together and just solve it in one go. And I'll show you what I mean by that. So what you can do is take f of 3, and remember that f of x is 3x squared minus 4. So writing f of 3 would look something like this. And then we're going to be subtracting g of negative 4. And g is that function up here, x plus 2 quantity squared plus x. So if we evaluate that at negative 4, we end up with negative 4 plus 2 quantity squared minus 4, or plus a negative 4 rather. Let me erase that, make that clear. Because it's up here it's x plus 2 squared plus x, and our x is negative 4, so we'll add a negative 4. Now we're taking these two functions and we're subtracting them. So it's going to be this whole thing, my f of 3, and we're going to subtract this whole thing, my g of negative 4. So over here, 3 squared is 9. And we're subtracting this entire thing. Negative 4 plus 2 is negative 2. Plus a negative 4 is the same thing as subtracting a 4. 9 times 3, whoops, let's change my pen. 9 times 3 is 27. And we're subtracting this whole thing. Negative 2 squared is negative 2 times negative 2, which is just 4. 27 minus 4 is 23. 4 minus 4 is 0, and we're subtracting these two things. 23 minus 0 is just 23. So, f of 3 minus g of negative 4 is 23. Alright, I'll just leave this here for a second. You guys can pause it, and then I'm going to erase. Alright, so that's function notation. You can take any of these things, no matter what it says, if it's talking about h of x, or f of x, or g of x. You can take any of these questions, whatever it's suggesting, and you need to find out which functions it's talking about and apply those to the situation. Cool? Alright, I'll give you a second to wrap this up, and then we're going to move on to our last topic, which is domain and range. Alright, so let's talk about domain and range. Well, domain is talking about all of the x values on a graph. So, for example, if I had a graph my domain would be talking about the x values, all of these numbers along the x-axis here. My range would instead be talking about the y values on the same graph or the same function. So all of these along the y-axis. So now let's talk about what that means. Let's talk about it as a graph. Let me erase this. There were a couple on the study guide, fake exam, that threw people off. So let's talk about the first one. Oop, I don't want to do it in red. Boom. Alright. So the first one didn't have any numbers. The first one did something like this. And a lot of people said, Chris, there are no numbers. Should we make up numbers? Or how do we answer this with no numbers? Well, we have to think about what exactly domain and range mean. Remember that domain is talking about all the numbers that we can plug in to this function, or that are graphed by this function in this case. And so if this graph just continues to go in both directions, we can see that it will never stop. It will keep going. So any x value along the x-axis from both negative infinity way out here to positive infinity way out here are going to be on this function. Like, this function will have values there. They're going to be huge or really, really, really negative, but they'll be there. So there is no limitation to this domain. It just keeps going up and to the right and down and to the left. So our domain goes from negative infinity to positive infinity, because we can keep plugging in smaller and smaller negative numbers here, and it will keep finding a point down here somewhere. And we can keep plugging in really huge positive numbers and it'll find some point up there. So we can plug in any of those numbers. The other way you could have written this is this. I saw a lot of people write either this or this. It is not 1R, it is not IR. It is an R with an extra backbone, a double bar. So you just write that by writing like a Roman numeral 2 without the lines on top, and then you just turn it into an R. Now if we look at range, range is the Y values. And again, we're going to have the same situation. This keeps going up and up and up and up and up forever, but also at the same time on the other side of the graph, it goes down and down and down and down forever. So it will keep going up to infinity in the upward direction and down to negative infinity in the downward direction. It'll take it a while to get to infinity, since infinity is not really reachable, but it will keep going in both directions, which means it goes from negative infinity to positive infinity, or all real numbers. You will find that most of the graphs that you guys are familiar with, that you've done, that are extended on the ends here with these little arrows, will go on forever. That's just kind of how they are. So let's move on to a different example. If you need to pause here, go ahead. So the next one is a really popular example when talking about domain and range, and that was a parabola, I believe. Let's say it is here. So if we look at the domain, there are no restrictions to our domain. Our domain keeps going. If we extended out this x in both directions to infinity, negative and positive infinity, you would see that this eventually will get there. This parabola climbs slowly, but it never goes actually straight up. It might look like it's going straight up, but it's never actually going straight up. In reality, it's still going out to the right a little bit. And so eventually it will get to whatever numbers we plug in down here. It will eventually get there. The same with the negative side. This never ends up going straight up. It's still, even though mine doesn't look like it's moving outward, it is still moving outward, just very slowly. And so eventually it will get to where we need it to go. So its domain is all real numbers, or negative infinity to positive infinity. Its range, however, is a little bit trickier to figure out. For our range, we have to consider all the possible y values that fit on this graph. Well, this y value goes up to positive infinity. It just keeps going up and up and up. So we know that it's going to end at positive infinity. That much is clear. Where it starts is a little bit trickier. See, let's say that this point is negative 3. So it's 0, negative 3. There's this point here. It can't go below that. So this might be the graph. This might look something like this. When x is 0, we get negative 3, which we'll say is this down here, which is our lowest point. We can't plug in a number. There isn't an x value that will go below negative 3. Because if we plugged in, so if we plug in 0, we get negative 3. If we plug in a value smaller than 0, we end up with negative numbers. And the problem is when you square a negative number, it becomes positive. So, for example, if we plugged in negative 2 squared would be 4 minus 3 would be 1, and so our point would be up here. Or up here, actually. Sorry. So essentially, you can't plug in a smaller number into x and make this y value smaller, because when you plug in a negative number in for x, you end up with a positive number. And so the lowest point here is at 0, negative 3. And so our answers can only go from -3 and up. We can't ever get a number smaller than -3. So our range here is going to be -3 to infinity. And you can put parentheses around these or not. We haven't, as a class, talked about when to use parentheses or brackets. So if you use parentheses, if you use parentheses, I'm not going to knock you points off, but you don't have to. All right, let's talk about in a function. In a function, it works much the same way. When you have a function and you're trying to determine domain and range, not much is different. So let's say you had let's see. Well, this was a good one. I like this one because this is kind of a tricky one. So let's talk about domain and range. Well, if we think about the domain, if you think about the domain of this function, we got to think about what numbers we can plug in here. Well, I can plug in huge numbers. I'll get 2 answers. That's totally fine. Whatever. So this actually isn't a function. The domain of this equation, rather. I can plug in gigantic positive numbers and be totally fine. So this keeps going into positive infinity. That much we know is true about our domain. We can plug in huge 1 billion trillion gigantic numbers and we can get an answer, or 2 in this case. So we know that it goes off into positive infinity. We can plug in 0, so we know that that's not an issue. But when we look at negative numbers, we can't actually take the square root of a negative number. For example, -4. There isn't some number times itself that will equal -4. There isn't some number we can take and multiply it by itself to get -4, because -2 times -2 is 4, not -4, and 2 times 2 is 4, not -4. So there is no number we can multiply by itself to get -4. So negative numbers actually become an issue when we're talking about square roots. So the domain is going to go from 0 to infinity. Now when we look at the range, we have to think about all the answers we can get. Well, because it's a square root function, if I were to plug in 4, my answer would be both 2 and -2. So my graph at 4 is going to be 2 and -2. And we talked about this in the earlier example with the table. If we do the square root of 9, we'll have 3 and -3. So our graph is going to just do something like this. Off into the night. So you can see the domain here. We can't have anything less than 0 as our x value. It won't work with our equation here. So you can see our domain is all of these values, 0 to positive infinity. Our range, well, our numbers keep getting bigger and bigger and bigger up to infinity, and smaller and smaller and smaller down to negative infinity. These will just keep going. And so our range is going to be all real numbers, or negative infinity to positive infinity. Alright, and that's going to be the end of our study guide. Again, the methods I've shown you should work for all of the questions you'll see. The main ideas are you need to know how to determine whether or not something is a function by measuring whether or not it has one output for each of its inputs. Remember that each output can have multiple inputs, but only each input can only have one output. So really you're just looking at the x values. Do the x values have one answer, or do the x values have more than one answer? That's the way you're going to determine if something's a function. For function notation, remember that you first need to evaluate which equation it's talking about and then plug in the evaluated number. For domain and range, you need to think again about input and output. You need to think about what are all the possible numbers that you can plug into a function or into an equation. Are there any limitations on what you can plug in, such as our x squared, or our square root of x example here? There were some issues. We couldn't plug in negative numbers there, so that affected our domain. For range, you need to think about the kinds of answers you could get. So for example, if we had this, well, our range would be something crazy, because if you think about our answers, or our domain, excuse me, if you think about our answers for our domain, we think about what we can plug in here. Well, we can't plug in 0 because that makes us all crazy. So we can plug in gigantic negative numbers, so we can go from negative infinity, and we can get to 0, but we can't actually plug in 0. And then also we can go from 0, even though we can't plug in 0, to infinity, positive infinity. And the range for this function, well, if we think about it, if we plug in gigantic, huge numbers, for example, 1 over 10,000, this is going to be a very small number. 4 divided by 10,000 is so tiny. So we can get really tiny numbers and really large numbers if we plug in 4 divided by 0.00001. That's going to be a huge number. 4 divided by 0.00001. That's going to be a huge number. But the thing is, we can never get to 0. So our range, again, would have an issue, just like our domain, or it can never get to 0. This isn't going to be on your test, but it's important to think about what answers you can get as your range, and what values you can plug in as your domain. Alright, I hope you have a good test. It's on Tuesday. Have a fantastic weekend. Again, if you have any questions, you can email me or Addie. I'll write up my email here. Excuse me. Or you can leave me comments on the YouTube video. I don't mind that either. If you have any questions. If you have any feedback for me, also please feel free to let me know. I've just changed the video to use a dark background with a light writing. A lot of people said that that was clearer to them. My email is christopher.hickson@tusd1.org. Alright, take care everyone. Have a good day.